Afternoon, nerds. Today, we're going to move on to actually the next two sections, not next one section, next two sections. Lesson 9.9 and 1.9 and 1.10. Still working on rational functions. We've already discussed vertical asymptotes. We're going to dive a little bit deeper into them. But now we're actually going to discuss how we find and recognize holes in these graphs. So I could read it verbatim, I guess. We have defined a rational function as the ratio of two polynomials in earlier lessons. Defined the zeros of the function in the last lesson, and specifically the zeros were what makes the top equal 0. So if you can make the numerator of a fraction equal 0, then the whole fraction equals 0. The domain for all polynomials is the same, all real numbers. However, the moment you put a polynomial in the bottom of a fraction, now you have to worry about its zeros because you're never allowed to divide by 0. Big time no-no. So dividing by 0 in rational functions causes one of two things. Either A, a hole in the graph, or B, a vertical asymptote. Vertical asymptotes occur when a factor in the denominator does not cancel out with factors in the numerator. So I don't like this. What is this? That is x equals 0. I don't really understand what that's saying. So essentially what we're going to write is the 0 of the denominator, 0 of the simplified function's denominator. So let's write it like that. Vertical asymptotes are going to occur at x equals 0 of simplified function's denominator. So after you've done all your simplifying, if you still have a number that makes the bottom equal 0, there will be a vertical asymptote at x equals that number. So x equals 0 of simplified function's denominator. All right. So then what identifies something as a hole in the graph? Well, if it would have made the denominator equal 0 in the original setup, but through the magic of canceling, it no longer makes the denominator equal 0, that is a hole in the graph. Basically, if it canceled out. So this is going to happen at x equals 0 of canceled factors. In the denominator. So they're canceled. That means they no longer make the bottom equal 0, but they used to. That's how you know there's a hole in the graph. Boop! Here we have a rational function, and what I see is no factors cancel off the top and bottom. And I do see that there is a number that makes the denominator equal 0. X equals 2 is the vertical asymptote. Because that makes the denominator equal 0. And you can see it's right here. X equals 2, vertical asymptote. It's old knowledge, but check out where this thing crosses the x-axis. At -3. That's the 0 of the numerator. So zeros of the numerators are zeros of the function. Real zeros of the numerator will be x-intercepts. Because remember, zeros don't have to be real, but real zeros of the numerator will be x-intercepts. There. Now let's check out this graph. Once everything is factored and we get it to here, what you can see, I hope, is that x minus 3 is a factor of the top and the bottom, which means it could cancel out. This thing would then simplify to 2 x minus 1 over x minus 2. Before I did any canceling, there were two different numbers that made my denominator equal 0. Those numbers were x equals 3 and x equals 2. In the simplified version, there's a single number that makes the denominator equal 0. That means I lost a 0 of the denominator. Since I lost a 0 of the denominator, I know there's a hole at that number, at x equals 3. This one still has an asymptote, though, a vertical asymptote at x equals 2. It's right here, because x equals 2 makes the denominator equal 0. But x equals 3 used to make the denominator equal 0, and now it does not. There is a hole at x equals 3. But notice, please, that the hole is a single coordinate. That means it has a y value. Anybody remember from Algebra 2 how to find the y value of that hole? Plug what into where? Hold on. What number? What x value? In this one, in this example, plug in what? He's on to something. We're plugging something in here. But what number are we plugging in and where are we plugging it in? He says, wait. He says, wait. We're waiting. Okay. So we're going to plug in x equals 3 because that's the 0 that got canceled. And where do we plug it in? Which function? I have it here twice. I have it here unsimplified and have it here simplified. Into the simplified one. So all you have to do is take the x value that you're actually not allowed to use and plug it into the simplified function. You see, you can't plug it in here. If you try to plug it in here, you're going to get 0 over 0. And that's big time no-no in mathematics. But if you plug in x equals 3 into this, you're going to get, let's see, 3 minus 1, which is 2. 2 times 2 is 4 over 3 minus 2, which is 1. 4 over 1. Oh, look, there's the y value. Y equals 4. So if you want to know the y value of a hole in the graph, you evaluate the simplified function at the canceled 0. In fact, boop, if you come down here, there's instructions for finding the coordinates of the hole. It's going to be, and I already wrote, x equals, we've already wrote this, but I'm writing it again, 0 of the canceled factor. Plug that x into the simplified function to find y. There. And how do we find vertical asymptotes? Well, we've already read up top, but we have a box for it here, so we might as well write it. It's the 0 of the simplified function's denominator. X equals the 0 of simplified function's denominator. Awesome. Limit notation of end behavior. Well, that's actually a typo because limit notation of end behavior is here. By definition, end behavior is what happening when x is getting outrageous. So this isn't supposed to say end behavior. This is supposed to say asymptotic behavior. Limit notation for asymptotic behavior. There. And then, you guys know Barry Wimbish? He noticed last period, Barry Wimbish, Hey, notice last period that this arrow and this arrow actually pointing the wrong direction. And you thought maybe that was some kind of new math symbols. No, those arrows are just backwards. So we're just going to go ahead and fix those. Those arrows are backwards. There we go. All right. So now that we've fixed the boo-boos, how do we recognize asymptotic behavior? The way you recognize asymptotic behavior is when x approaches a number, and it doesn't matter if it approaches it from the left or from the right. If the y values go to one of the infinities at certain values for x, then you have found an asymptote, a vertical asymptote. So one more time. If the limit of your y values is one of the infinities when you're on either side of an x value, you have found a vertical asymptote. Graphs will always go to one or both of the infinities at vertical asymptotes. That's how we recognize them using limits. Then it's got here the limit notation for end behavior, but we already talked about that. I covered that yesterday and the day before, actually. The definition of a horizontal asymptote is limit as x approaches one or both of the infinities equals a number. So if it equals a number at the infinities, you found a horizontal asymptote. And something that shocks me that didn't make its way onto these notes is, what is limit notation at a whole? You see, you've already done it. You did it in the homework for 1.7. But it doesn't show up anywhere in the notes. So let's get limit notation for this hole in this graph. The limit as x approaches the number 3, because that's the x value where it's happening, from the left is equal to, so if you're to the left of 3, you'd be doing this. It's heading towards the y value of 4. Because I'm to the left of the hole, but I'm getting closer to x equals 3, I'm approaching this y value. And the limit as x approaches 3 from the right side of 3. Okay, so that's over here. As you can see, my y values are once again approaching 4. So how about a nice little bow on all of it as a concept? Ready? If your graph approaches an infinity at an x value, vertical asymptote. If your graph approaches a number from either side of an x value, hole in the graph. If your graph approaches a number at the infinities, horizontal asymptote. And you must have an understanding of those three concepts to be highly successful in this material. And in period 7, last period, I actually wrote it like this. Now you don't have to have this written, I'm just showing it so it makes its way to the video. Asymptotic behavior, the limit as x approaches some number, and I don't care if it's from the right or the left, that doesn't matter. If it approaches one of the two infinities, I don't care which one, you have a vertical asymptote. But in order to be able to identify a hole in the graph, you have to be able to say that as x approaches some number from the right and from the left are going to give you the exact same value. That's how you know there's a hole there, because they're going to give you the exact same value. And whose homework number 7 is this? No, I don't want to use that one. That's not a good example. Let's see if I can find a better one. Someone who did it right. There's one. We'll keep his name off the paper, off of the notes. But this is your homework number 7. Look, as x approaches 3 from the left and 3 from the right gave me the same number. Without this picture, I could tell you there's a hole at x equals 3. And the coordinates of that hole is 3, 1. Oh, look, there it is, 3, 1. So you've already done it. You just didn't realize that we were building up to the limit behavior of knowing what a function is doing just by looking at its limits. Guys cool with all that stuff? Yes? No? Maybe so? You have a question? You kind of have question face. No? Okay. Just making sure. Then let's flip the paper over. and head on over to the back where we got lots of words. The first sentence is just reminding you what it means to be in lowest terms. Lowest terms means nothing else will cancel out. That's what lowest terms means. It says you find x-intercepts by setting the numerator equal to 0, because like I said, if the top of a fraction equals 0, then the whole fraction equals 0. Wholes and vertical asymptotes both happen at what makes the denominator equal 0. But specifically, vertical asymptotes happen at zeros of the denominator when it's simplified. Wholes happen at zeros of the denominator that get canceled out. Okay? So, some tips to keep in mind. Simplify rational functions by always doing what to the numerator and denominator? What do we always do to them at the very beginning? My favorite F word to say in school. Factor, yeah. A couple people whispered it. We're going to factor both the numerator and denominator. You need them factored because that's how you find the zeros of everything. Oh, oops, I gave you the next answer. Find the zeros of both the numerator and the denominator. If a 0 is common to the numerator and the denominator, like if you had x plus 2 on the top and the bottom, what could you do with it? Cancel out. So if it's common, it cancels. If you have a 0 that cancels from the denominator, what have you found? You have a hole. You have a hole in your graph. But if a 0 is unique to the denominator, meaning it doesn't cancel, since it doesn't cancel, it'll be in the simplified version. What do you have there? A vertical asymptote. And if 0 is unique to the numerator, that's the top. 0 of the top is what? A real 0 of the numerator is an x-intercept. I'm actually very surprised it doesn't say if a real 0, because polynomials can have complex zeros, but by definition a complex 0 is not a place where your graph crosses the x-axis. Only real zeros of the numerator will be x-intercepts. Are you ready to analyze some functions without their graphs? Yes, ma'am. Okay, great. Let's go to it. I'm going to kind of ignore the directions. It says determine x values of holes of vertical asymptotes. You know what we're going to do? We're going to find the x values of vertical asymptotes, the coordinates of the holes in the graph, and, even though I didn't ask for it, the zeros of the function. Just so we've got all of that knowledge on here. Cool beans? You guys are awfully quiet today. Okay, well, luckily for us in part A, everything's factored. So let me grab a handy dandy pin here and notice that x minus 4 is on the top and the bottom, so it cancels out. My function will simplify to x plus 2 over x minus 3. Awesome. In green, you know what? Let me grab my red pen first. There is a 0 of my denominator after it's simplified. What is going to happen if there's a 0 of the denominator in the simplified form? Vertical asymptote. So you have a vertical asymptote at x equals positive 3. That is a no-go for this graph. So what happens at x equals 3? The graph approaches one or both of the infinities. That's what happens as x gets closer and closer to 3. And I'm pretty sure it's left side down, right side up of that asymptote. Now, I crossed off x minus 4. That means that x cannot be 4. X cannot be equal to 4, but the simplified version doesn't show me that. So what is occurring at x equals 4? A hole in the graph. I want the y value also, though. How do you find it? Like, okay, you plug it in. So you take x equals 4, and you plug it into the simplified version of the function. I'll use quotations because I'm not actually evaluating at 4. I'm plugging it into the simplified version over here. So I'm getting 4 plus 2, which is 6, over 4 minus 3, which is 1. I get 6 over 1. Okay. No, look what happens if you try to plug it into the original. 0 times stuff over 0 times stuff. It's super 0. Yeah, if you plug it into the original, you get 0 over 0. And that'll be true for every hole. Because the only reason why it crossed off is because it was on the top and the bottom. It's super 0, he says. Yeah, 0 over 0 isn't even undefined. It's something even worse in mathematics. It's called indeterminate. There are several things in mathematics that are considered indeterminate forms. Like, you guys know that everything to the 0 power is 1, right? Except for 0 to the 0. That's indeterminate. Except for infinity to the 0. That's indeterminate. Right. No, because infinity is not a number. So infinity to the 0 cannot be 1. It's an indeterminate form. It's just like saying infinity plus infinity. Indeterminate. Infinity divided by infinity. Indeterminate. Infinity raised to the infinity. Indeterminate. It's like there's a lot of things in mathematics that make you think you know, but you actually can't ever know. Well, that's not true. You can know, but you need some calculus knowledge, depending on the setup. All right. Last but not least, there is a 0 of my numerator. That is going to be an x-intercept. Now this next one, it confused some people in last period. So I'll tell you what I'm going to do. And you don't have to do this, but I'm going to do it for note-taking purposes. I'm going to fully expand this thing. It's not necessary that you do this, but for good notes, let's go ahead and do it. Now we can simplify. I noticed that there's an x minus 1 on the top and bottom. I also noticed that there's an x plus 3 on the top and bottom. My function simplifies to x minus 1 over x plus 3. So then I ask you, is there a 0 of the denominator in the simplified version? Yes. Since it's a 0 of the simplified denominator, what is it? No, not what is the number. The number is -3. But what is it? What kind of structure is it if it's a 0 of the simplified denominator? It's a vertical asymptote. See, the 0 of the simplified denominator is a vertical asymptote. I don't care that I crossed off an x plus 3, but Mr. M, I thought you said if you cross it off, it's instantly a hole. Well, that's only if it no longer exists in the denominator. But x plus 3 is still hanging around. That shows me that x still can't be -3, even though it's simplified. That forces that to be a vertical asymptote. There used to be a 0 of the denominator at x equals 1. Is x equals 1 still a 0 of this denominator? Does x equals 1 make this denominator equal 0? No, it doesn't. It makes the numerator equal 0, but it doesn't make the denominator equal 0. That means you have a hole at that x value. Now let's plug in x equals 1 to our simplified version. 0 over 4. Oh. Is there an x value that makes the numerator equal 0? Ah, yes, there is at x equals 1. So is that an x-intercept? It can't be, because there's a hole in the graph there. So because the hole in the graph is right where the x-intercept wanted to be, this graph has no x-intercepts. Let's just be really clear about this. If this was the original function, yes, it has an x-intercept at 1, 0. Yes, it does. But you have prior knowledge of this function, and you know that x equals 1 used to make the denominator equal 0. That means the graph can't exist there. It's literally a hole in the graph. What you think about that one? Yes. So no. So there are two numbers that make the denominator equal 0, right? In the original setup, x equals 1 and x equals -3. So what we do is we go to the simplified version and we ask ourselves, well, what's going on with those two numbers? At x equals 1, oh, this doesn't say I can't use x equals 1 anymore. That guarantees that there's a hole there. But I still can't use x equals -3. It's going to make me divide by 0 still. That means that's a vertical asymptote. And you're not going to have holes on your vertical asymptotes because they're just places the graph doesn't exist. All right. More questions about that one before we do the next one? None. Okay. We need to factor this. There's a GCF in the denominator of x. Well, after you factor, you're supposed to figure out what makes the denominator equal 0. After you're done canceling, obviously. But well, you would figure out what makes the denominator equal 0 to figure out where your holes and asymptotes might be. So let's figure out what makes the denominator equal 0. What makes it equal 0 right here? Okay. This is the simplified version. So since it didn't cancel out, what kind of structure is there? Since it didn't cancel out, and I'm not allowed to use x equals 0 because it would make me divide by 0, what is it? A vertical asymptote. Look, if it makes the denominator equal 0 after the simplification, then it is a vertical asymptote. There is no simplification to do that makes x equals 0 a vertical asymptote. Oops. Why isn't he asking me? Why isn't it what? Why isn't that not a hole? Because look at where the holes happened before. Let's look to this original one. The hole happened at x equals 4 because I was able to cancel it out. And because if you look to the simplified version, you're allowed to plug in 4 now. Because you were not originally allowed to plug it in, but then after simplification you can, that makes it a hole. Now here, you can't use x equals 0, and nothing is even simplifying. Vertical asymptote. How about this? What makes x squared plus 5 equals 0 in the real number system? Nothing. You know why? Because you can't get a negative out of a square in the real number system. This isn't possible. This part of the denominator does not generate any no-nos for us. Every x you plug into this set of parentheses comes out a positive number. It'll never be 0. So we're in good shape. The smallest number that will ever come out of these parentheses, 5. And that's only at x equals 0, which you're not allowed to use. So did any x's cross out? No. Then there are no holes. How about this? What makes the numerator equal 0? Say that again for me. Nothing. So there's no x-intercept. There you go. It's got a graph with a vertical asymptote at x equals 0, which is the y-axis. Oh, and by the way, since this is bottom heavy, the x-axis is a horizontal asymptote. So this thing has asymptotes at the axes. So not only does it not have an x-intercept, it also doesn't have a y-intercept. Because if you're on the y-axis, x is 0, right? Well, you can't use x equals 0. So that graph doesn't touch either one of the axes. What's it look like? I'm not sure. But I know it doesn't have any holes in it, nor does it have x-intercepts. Ready for the next one? We're going to factor everything we can. Both the numerator and the denominator factor. The numerator is the difference of two squares. X squared minus 9 will factor to x plus 3 times x minus 3. Denominator. Two numbers that multiply to negative 6 and add to 1. Negative 3 and positive, no, excuse me, positive 3 and negative 2. Positive 3 and negative 2. Okay. X plus 3 and x minus 2. Looky here. This one does simplify. In the original setup, there were two x values that made the denominator equal 0. In the simplified version, there's a single x value that makes the denominator equal 0. What does that always guarantee me is going to occur if there are now less no-nos? A hole in the graph. And since there is still a number that makes that denominator equal 0, I'm also guaranteed a vertical asymptote. At what makes the denominator equal 0? 2. There will be a hole in the graph at what used to make the denominator equal 0. What used to make the denominator equal 0 now doesn't. Negative 3. And if we want the y-coordinate for this hole, which I know that's more than what the notes have asked for, but I think it's great to know how to do it, is to take that negative 3 and substitute it into the simplified version. Negative 3 minus 3, that's negative 6. Negative 3 minus 2, that's negative 5. Negative 6 over negative 5 is 6 over 5. And lastly, is there a number that makes the numerator equal 0? Absolutely. That means there is an x-intercept because it wasn't a hole in the graph like we experienced here. So we have an x-intercept at x equals 3. Look at all that stuff. Man, that's good stuff. No graphs, but we can sure tell a lot about these things, can't we? All right. Questions, comments, concerns on that before we move on to the next skill? All right. Boop! The next skill is going to be figuring out the equation of a rational function just by looking at limit notations and what those limit notations tell us. I'm only going to do part A. We'll do part B tomorrow. We'll do this example tomorrow. We're just going to get through this one. So let's check it out. This says, as x approaches 2 from the left, my y value approaches 3. As x approaches 2 from the right, my y value approaches 3. What does that tell me I found? A hole in the graph. What are the coordinates of that hole? What x value does the hole occur at? 2. And what is the y value there? 3. So we have a hole at 2, 3. That says ho. Hole at, I forgot my L. Take this L, ho, become a hole. Let's see, hole at 2, 3. All right, well, hey, the fact that I know a whole occurs at x equals 2 tells me that my function don't write too large, must have had an x minus 2 cancel off the top and the bottom. And what about this? As x approaches -4, from either side, my graph goes to an infinity. So what does that tell us? Vertical asymptote at, there you go. Vertical asymptote at x equals -4. That means the number -4 makes the denominator equal 0, even after you simplified it. There must have been an x plus 4 in that denominator. Yes. X minus 2. Sorry, I'm trying to write small because I know I need some vertical space to do a little bit of work. Now we know that if we simplify this thing, right now it looks like 1 over x plus 4, right? But look what happens if you plug in x equals 3 to that. You get, x equals 2. Look what happens when you plug in x equals 2 to that. You know if you plug in x equals 2, you're supposed to get the y value of 3, right? You'll get 1 over 6. You were supposed to get 3. What that tells us is there must be a vertical stretch or shrink going on up here. And we have to solve for that vertical stretch or shrink. We know that the x minus 2's cancel out, right? And this thing simplifies to a over x plus 4. And what we know is, if we plug in 2 to this x with an a over it, we better get this y value. So we know that a over, remember the green stuff is canceled, 2 plus 4, which is 6, equals 3, because that is the y value of the whole. So what does a have to equal? 18. You multiply both sides by 6, and what you get is there is a vertical stretch or shrink of the number 18. That's a big boy. I'm going to use the bottom line of this table as my fraction bar. 18 x minus 2 over x minus 2 times x plus 4. Now we have now guaranteed that we have a whole at x equals 2. We've guaranteed that when we plug in 3 to the simplified version, we will get 18 over 6, which is 3. And we've guaranteed that -4 makes the denominator of the simplified version equal 0. That's the whole thing. Question for me? You figured it out. Are there any questions for me that haven't been figured out yet for today? Yes, ma'am.
So, did you get the 6 from the denominator?
So what I did was, remember to get the y value of the whole, we plug in the x value of the whole,
Okay.
of the simplified version. So I plugged in x equals 2 to right there, which is why I did it in red.
Okay.
I did 2 plus 6. You're not plugging it into the green part because that cancels out. So you get some a value over, and you plug in the 2 that the pin is currently pointing at. 2 plus 4 got me that 6, but we know the y value had to be 3 there. And that's how we did it. Thank you, nerds. Appreciate you.